One last example for us, if we were to have the matrix A being -6, 9, -1, 0, let's think about what would happen here. Well, our trace is -6, and the determinant of A is, let's see, 0 minus a -9, so positive 9. And that means that if we were to look at our characteristic equation of when p of lambda is equal to 0, what we would get would be lambda squared minus the trace of A times lambda plus the determinant of A equals 0. In other words, lambda squared plus 6 lambda plus 9 is 0. And so we end up with lambda plus 3 quantity squared being 0, or our solution is lambda equals -3. I want to add that this is a solution of what we call multiplicity 2. What this means is that lambda equals -3 is a solution twice. The multiplicity is the power that you have for that quantity, in this case lambda plus 3. It's the power that you have in the characteristic polynomial. So when you factor it, you end up with lambda plus 3 quantity squared. So that squared tells you that this is multiplicity 2. Again, it turns out that if you have any polynomial of degree n, you're going to have exactly n solutions if you count multiplicity. So you have, in this case, we had -3 was a solution twice. And we know that we get 2 solutions because we have a degree 2 polynomial. So the sum of all the multiplicities, in this case it's just the one quantity, the sum of all the multiplicities has to be 2. Okay, so the sum of the multiplicities and the degree of the polynomial have to be equal. This is actually a famous result called the fundamental theorem. So the fundamental theorem of algebra. It's a tricky proof, but it turns out that it is true. Okay, fundamental theorem of algebra.